I can see that in your set of reactions of preparations of alkenes. Your teacher has discussed Wolff-Kishner reduction, has discussed Clemenson's reduction,
Yeah,
and all kinds of extra stuff.
yeah.
He's not wrong. Let's quickly talk about each of them. So go into Wolff-Kishner. Let me copy
Mm.
that off, I suppose. Let's quickly discuss the Wolff-Kishner and Clemenson's at least. So this is your synopsis for your alkanes, huh?
Yeah, I mean, there's more, but should I send the rest?
Send me the rest.
1 second.
Send me the rest of alkanes.
Previous. Okay.
Okay, so he's talked about Clemenson's also over here, I see. And he has been unnecessarily specific enough even to give these cases.
I sent the ones before it, and then
Yeah. So it's 5 pages totally for you.
oh no, there's more.
Huh?
There's more, sir.
There's more. Wonderful.
Yeah.
Wonderful. So from alkanes and alkenes and alkynes, from alkenes and alkynes, the Sabatier sentence. What is the key point there?
Sebastian. 1 second. The
How do you write a synopsis for that one?
mm,
In the
hydrogen will
short,
attack. Hydrogen bond initiates reaction where attacks double bond.
no, you're
Uh,
copying what I gave. Stop copying. Stop copying. Go with what your gut feeling tells you. You've seen enough examples of that now, right?
yeah.
At this time, your gut should be or your instinct should be a little bit more better than what it has been for organic, at least with respect to this reaction, right?
Yes, sir.
So
Yeah.
go. You put a whole
So
bunch of data there, compress it and
yeah.
tell me what would you do here. Hmm.
Mm, hydrogen under the presence of a catalyst, uh, like yeah, nickel, palladium, platinum, reacts with a saturated compound, and the hydrogen will attack.
Let's just call it as ene plus hydrogen gives N.
Yeah.
Now,
So this hydrogen goes and
how should you stop? Stop. How should you, what is the best way to represent this? You can think of it as pi bond and sigma bond are broken.
yes,
And you're going to be
sigma
having
bond is
two
created.
carbon H sigma formed.
Yes.
Fair enough?
Yes, sir.
So what will this information tell you?
Bond breaking and energies. It,
Released. Because you're breaking
released.
one pi bond and one sigma and you're forming two sigma, which is
Exactly.
more stable.
Breaking. Sorry.
Sigmas are more stable than pi, correct?
Yes, 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 yes.
So effectively, the more stable bonds are being formed over here. That means the product formed is more stable.
Yes.
So this is where the other piece of data which you should have learned from thermo actually will come into play better here. Let me give that to you separately here now so that you will remember it cleanly. If products are more stable,
And reaction will happen.
no, stop
Oh,
extrapolating. Let me give you the point. If products are more stable implies reaction is exothermic.
exotherm. Okay. Hmm.
Okay, yeah. If
Yes, sir.
reactants are more stable, implies reaction is endothermic.
Okay. Yeah.
Okay, yeah. But reaction does not happen only because of stability. There will always be two parts for any reaction to happen. One will be stability. What is the other thing? What is that you are doing now? You are attending classes, you are attending all of this, you are correct? For the
Yes,
sake
sir.
of the future being more stable.
Yeah.
What is the price you are paying?
Freedom.
Correct. So any reaction, there will always be two sides to check. Stability and freedom. Anything, any change, you'll always have two things to check: stability and freedom. So don't assume only one of them is going to be the key thing there. Of course, if stability is going to be something which is going to be better, that helps. Certainly it helps. If stability of products is better, it helps. In fact, you think and tell me, what will be the ideal case when the reaction will absolutely happen? What is your win-win situation?
Product is very stable and gaining freedom, and you're also gaining stability.
Yes, exactly. That is the best case, right?
Yeah.
So if you can get IIT without doing anything, best ideal case, correct?
Yes.
So that is something which will happen like this without any problems. Type of a change you can say will happen for sure. So any change or a process where the system is gaining in both stability and in terms of freedom by performing the change, it will absolutely happen. That change will absolutely happen. So that is the change which will definitely happen. Not something which is only gaining stability. If it is gaining stability, sometimes it might lose freedom.
Yeah.
So in this particular case, have a look here. Is freedom lost or is freedom gained in the process? Stability is gained by products, correct?
Yes, sir.
Absolutely, the products are gaining in stability. So exothermic, that part we have concluded now automatically. Okay, now what else is going to be the case here? What else can you conclude from here? You can technically look at the reaction and say that two substances have combined and become one.
Yes.
So what was originally two pieces which had freedoms individually are now one.
Losing more freedom.
Yes, that means they have lost some amount of freedom in the process for sure. Now that let's negate that. Let's not bother with that part. No, that will go into thermodynamics too much. Let's not touch that right now. Let's come back to the other things here, which you can understand here. So in this case here, you can see that you're going to be having a pi bond being broken and a sigma bond being broken. Correct? Huh?
Yeah.
So which bond is more tougher to break?
Sigma bond.
Correct. That means the catalyst is helping which bond break here?
H2.
H2. So the catalyst is acting on the H2.
Yes.
Okay. Now, next, what other pieces of information are going to be useful for you here?
It is cis addition.
Syn attack or cis attack.
Yes.
Which basically translates as same side attack.
Same side, yes. Yeah.
By, you can mention over here, hydrogen atoms.
Yeah, that is, yeah.
From surface of catalyst.
That layer thing, yeah.
That will basically end up covering a large amount of data which you need to cover off from that. Now, anything else which will help you in the process here?
Maybe something
about all of the data which you had over there. Let's have a look
this
at it now.
Optical active, maybe something.
Let us have a look at the data you have put in. Oh, you have sent me a whole bunch of pages.
I'll tell you which page. Yeah, there, yeah.
So now, do you really need that optical activity crap and all? Isn't that the purpose of having the Syn attack mentioned there?
Yeah.
Why don't you know that bullshit there then? I don't see the most important piece of information though here. That is a shock here. I see all kinds of junk here, but I don't see the more critical information which is necessary here. What is the necessary piece of information which is supposed to be there? Tell me. You mentioned the process as ene and ine.
Yes.
But I didn't see ine anywhere.
Oh, yeah.
I didn't see any mention of how it happens for iron there. So for iron, I'll be having same type of hydrogen here, 2 moles of hydrogen.
First
And
happens with conversion.
technically, in this process here, it is always best to mention how to stop it at in stage. I'm sure your teacher will discuss that also here.
Yes. Yeah.
So that would have been a more useful piece of information over here. So you can mention iron plus hydrogen in the presence of nickel or palladium or platinum. Directly gives you N. And we're going to be having 2 pi bonds, 2 sigma bonds, and 4 sigma bonds over here. Now, you can add this piece of data here, which will be useful here, which is that when you poison the palladium,
yes,
you end up having the reaction
only
stop.
in. Yes, yeah.
So you can mention this part here. This would be extra information, which is not going to be necessarily irrelevant here, but could add value to your synopsis part here. But I don't see that piece of data here. But I see a lot of unnecessary junk. All of this junk here, you have no need for it. You have no need for it. Optical activity, obviously you'll have optical activity happening whenever there's a chiral carbon happening, right?
Yeah. Yes.
Why do you give a crap about that beyond a point? Does that matter here? No. Another piece of data which is immaterial here. Optical activity. Why I'm saying optical activity does not matter here? You think and tell me?
In addition.
That is not the problem here. The attack is happening on an ene or an ion. That means it's a planar species.
Yes, exactly.
So what is the point of a planar? That means if it is planar, it can have both sides equal attack only, right? So do I need to really care about optical activity beyond a point here? No. Why? Because I'm going to get a goddamn racemic mixture. Right. Everything which is formed is going to get cancelled out anyway.
Yeah.
Optical activity, you can remember this very important key point. To get a final optically active mixture as product in a reaction must start with at least one optically active substance. It cannot be something which is optically inactive. You cannot start with something which is. Have you learned about this already, or you're not familiar with this point?
No, sir. I was not familiar.
In any reaction where you are going to be having any final product, final mixture as some optically active mixture as the product over there, you absolutely must start with at least something which is optically active in a pure form in the beginning. It cannot be a mixture in the beginning. It cannot be a racemic mixture. You start with a racemic mixture which is optically inactive, you will get a racemic mixture or something which is finally optically inactive.
Okay.
Only when you start with something which is pure will you get something which is optically pure. Or at least you have a chance of that. Sometimes even when you start with something optically pure, you will be getting only something which is optically inactive at the end. Now, let's come back to this here. In any hydrogenation reaction, are you ever going to be having anything optically active in the beginning?
No.
Again.
Yes.
How so?
Wait. Give me 1 second. No, you won't, sir. My bad. You won't. No, you won't.
I won't. Is that sure?
Yeah. No, you can have
amount of time now.
Sir?
You took a bit of time to think it through, na? In these cases here, when you're going to be starting with an ene, it can be optically active.
It can be optically active, yeah.
How?
So, I mean, you can have often, like one side you can have, I don't know, it can have a chiral carbon, no?
How so?
How so many?
So basically, some other carbon can be chiral there, basically, right?
Ah, that's what I mean. Yes.
That's the idea there. Some other
Yeah.
random carbon will be chiral in that case. There.
Anything in the corner can be, yes.
It's not going to be necessarily this guy, but it'll be some other fellow.
Exactly. Yeah. Yes.
So that location, even if it is chiral, if that location is pure, then you'll get a pure optically active compound in the final product there. Think for a second. Let's take a compound like that and discuss it.
Ah, yes, you will. Yes.
Tell me a compound like
Yes.
that.
This, I'll tell the name 1 second. 1, 2, 3, 4. Sir, 4 methyl, 4 ethyl.
4 methyl, 4 ethyl.
Yeah.
You're making it unnecessarily complicated, my kid.
Oh, yeah, no. You can just do that, yes. Yeah.
Right? Make it nice and simple, because the point here was not about this. I want to show you something else over here also. Let's say I'm using deuterium. Okay, if I use deuterium over here, what will I be getting as the product here?
You'll have C, that thing, CD, D, yeah.
Now, have a look at the products. How many chiral carbons are there on that guy?
2, 3,
What?
3, 3, sorry, 3, 3, 3, 3.
3 chiral carbons, correct?
Yes.
Relax, it's okay.
Yeah.
There is nothing wrong with making mistakes at this stage. The more you feel bad about it, the worse it is. Chill out, it's okay. These are I know what I'm taking here. I know you're going to make a mistake. That's why I picked this. So relax, it's okay.
Yeah.
So in this case here, you're going to be having this guy being formed here, correct? So now let's take this. Let me take that. I'm starting with the racemic mixture. R and S are present over here, both in equal quantity. That is, I'm taking that my starting reactant is in a racemic mixture.
Yes.
What will I be getting as a product there? This will be syn attack.
Syn, yes.
So it can be RR, that is at these two locations. It can be RR and SS obtained as one set of products. Or it could be RS and SR obtained as the other set of products. Correct?
Yes.
No, I don't see that in your face.
Wait.
Why do I not see that on your face? Why are you not convinced here?
SRRS, how is it possible?
Hmm?
How is SR and RS possible? Should be in the same. Oh, sorry, my bad. Okay. Depends on the, yeah.
So I can see now where your problems are coming. Your problems are with the R and R notation and the S notation itself.
No,
no, your problems are there. Your problems are there. You've assumed R and S mean something. They mean nothing. They are just notations.
What I was thinking, I thought since both are deuterium, they'll have same. So
they don't mean anything. So you will be having RR as a possibility along with the SS. Let's say it's attacking from top. Then you'll get RR, let's say. That means if it attacks from the bottom, you'll get SS.
Okay, yeah.
And if on top attack, if it is giving you RS instead, then it will be giving you bottom attack SR.
Okay, understood. Yeah.
So if I had this original fellow as an R and an S both being applicable, then my products formed are R, RR, or S, RR, and R, SS, and S, SS. Correct?
Yes. Yeah.
Have a look here. All of them are formed in equal quantity technically?
Yeah.
Because this and this are equally possible. And this...
Since these also must be equally.
You're understanding the game here now, correct?
Yes, sir.
So we'll have these two cancelling. And we'll be having these two cancelling.
Understood, yeah.
So even though we are getting optically active products obtained there, we are going to be getting two sets of racemic mixtures.
Okay.
which means the final
Yeah.
mixture will be optically inactive still.
I see.
Just like how the initial mixture was optically inactive.
So, but you said it could be optically active.
Let's take an optically active and then see. I took a racemic mixture now, correct?
Oh yeah, you assumed it's a racing mixture. Yeah.
Yeah, I
Yes.
took a racemic mixture there, correct? That's why I had R and S to be equal.
Yes.
Now let's say I'm taking R alone. What will I be getting then?
R and then you get
R milega. And what else? R,
Sorry,
SS.
RSS. Yes.
Correct. I'll be getting these two. Or
Or
I'll get these two.
or RR or RS
Yes. Or I can
RSR.
get, sorry, not this one. Sorry, my mistake there. Or I can get RS or
RSR.
SR. Now, what is the relationship between these two guys here?
They are enantiomers.
Are they?
No. They are diastereomers.
Good. So these two are diastereomers.
Those are also diastereomers.
Good. So can these diastereomers cancel each other's optical activity? Will they?
No.
No. That means my product mixture now, is it optically active or inactive?
Active.
Correct. So if I start off with an R in the beginning, my product mixture will absolutely be optically active.
I see.
In this case, not always necessarily. So if you want to get an optically active mixture as the product,
Reactant must be optically active.
something in the reactants, I don't care what reactant, something in the reactants must be optically pure.
Yes. Yeah.
Properly optically active.
Correct. Yeah.
You understand the meaning of the sentence? The inverse is not true. If I start with optically pure, I can get optically inactive.
Yes, sir. Yeah.
Samajh raha hai na clearly?
Yes.
Okay. Now, next thing here. Let's come back to the next piece of thing which I want to talk about. Let's go for your synopsis again. So in this here, the entire crap over here is useless. That is all of the stuff which you see here. Let me point it out here. All of this. Most of this. The heat of hydrogenation automatically comes into play from the stability of alkene. So this point is something which is relatively useful. So, but this point doesn't cover everything also. Why does it not cover everything? Because you have not mentioned enough data there. You have mentioned half-ass data there again. What would be nicer to mention here? It will be nicer to mention that more pi bonds broken implies greater heat released.
Yeah, I wrote that.
Where was that?
Right there.
Where, Kana?
Beneath the heat of hydrogenation, number of pi bonds.
Oh, there is number of pi bonds are there. Oh, I thought it was good. Sorry, I didn't notice that properly. My mistake there. So you have written it down properly. My mistake here. You have put it down clearly. Fair enough. So that central bit definitely would be useful. That is this central bit. Yeah, this is something which you can definitely add here. But once you have put this in, the remaining stuff is useless. You understand what I mean by that? That is, most of the remaining stuff is not necessary here. What you have done there is effectively add data which doesn't really add value to you in this particular case here. 1 second, wait. This is now in a... In this case here, these deuterium reactions, are they really required?
No.
Is this erythro-3O nonsense really required?
No. Nothing.
And all of this stuff over here, which is going to be talking about, what to say, all of these changes here. Most of these are not necessary here. Now, this part seems like it is necessary, mainly for the sake of one particular thing. you want to add unnecessary extra detail, you can add it in, but that is what the fuck, mosquitoes. Chalo. So you can add it in, but that is not going to be something which is going to be adding value for you at this stage. In the sense, abhi ke liye synopsis likh raha hai, avoid adding unnecessary extra information like this. You can add it in, but it is going to only complicate the game here. Now, why is it complicating the game? Because you have to add in one mechanism point over here to show this thing there. So that is what complicates the situation over here. And that is not necessary now. It is not necessary now. When you're writing synopsis, avoid extra stuff which is going to be adding unnecessary extra layers of complexity. If something is making your thing more simpler and more cleaner to remember and more cleaner to understand, that's good. If something is making your thing more complicated, avoid.
Now, how do I know which one are actually needed and which are not?
See if it is going to be something which is going to be directly linkable to something extra. In this particular case here, how do you know whether this is going to be meaningful information to add at this stage or not? You have done hydrocarbons questions now, correct? How many questions did you see them using this stuff?
None.
That gives you the answer.
So then where is it useful?
You really want an answer?
It's fine, actually.
No, it's not a wrong question to ask. You have to ask those questions. It's going to be useful because in your internal exams, they will definitely ask that to you.
Okay.
They'll purposely ask that. I'm not against your teacher giving you this year. Ideal, I would have also given. So, this is something which has to be given here because purposely in unnecessary questions, they will give you this. And they are not wrong about it. So you'll have to accept that as well. But it doesn't mean you have to give that information at this stage. You can put that into yourself for a later time. Don't add it in now. So at this stage here, you can technically add it in, but it is not worth it. Skip this kind of information. It is not really going to be that useful. Now, the next bit over here is going to be, actually, no, there is no other next bit. This is basically this reaction completely. Let's go for the next reaction now. So hydroboration reaction.